Here is section 1.4, separation of variables and applications. We first define a separable differential equation. So it's first order. You'll have dy dx equaling some function of x and y. And we say that it's separable if that function of x and y that dy dx is equal to can be written as a product of a function of x and a function of y. So an explicit function of x and an explicit function of y. So mathematically we could say that that function uppercase h of x, y is equal to g of x times h of y. So there's a unique function of x, g of x, and a unique function of y, h of y. So it would follow that dy dx would be g of x times h of y, which if we express h of y as 1 over f of y, we get g of x over f of y. And at that point, it's not really cross multiplication, but you can think of it that way. We basically have dy dx is g of x over f of y. And if you express it in differential form and then multiply by f of y, you obtain the function of y with the dy and the function of x with the dx. So that's our goal, is to get the y's with the dy's and the x's with the dx's, and then we say that the variables are separated. So we're going to look at some examples, but make sure you understand that when we say explicit solutions, we mean to solve for y explicitly in terms of x. So here's our first example, and we first need to obtain standard form, which is dealing some function of x and y, so we'll need to transpose this 3x squared y, so that becomes minus 3x squared y. Now, it's actually a definition of differential form that if y f of x, the differential dy is f prime of x times the differential dx. This is literally a definition for differential form. And if you took the intermediate step to write d equaling f prime of x, it almost looks like we're multiplying by the dx to get this differential form. But these are really not fractions, and that's not what's actually happening. So understand that it's a definition of differential form where we can write now that dy is negative 3x squared y times the differential dx. And in order to gather the y's with the dy's and the x's with the dx's, here algebraically we could divide by y, so you could show that explicitly as I've done, or just mentally. And I'm going to write this as 1 over y times the differential dy equaling negative 3x squared times the differential dx. And then at that point, we have y's are with the dy's and the x's are with the dx's. So therefore we can integrate. Now if you want to show the integral symbol, integrating each side, that's fine. You don't have to. You could just jump right into the integration. And then on the left hand side, you need to, of course, recognize the formula. In general, the integral of 1 over x with respect to x is the natural log of the absolute value of x plus or constant of integration. And so therefore, 1 over y with respect to y integrates to be the natural log of y. And we don't need to include the absolute values we'll assume that y is positive, and then integrating minus 3x squared, we get minus 3x cubed over 3, or minus x cubed, and we add our constant of integration at that point. And I'm going to call that, because on the left-hand side, we generated a natural logarithm, I'm going to call that the natural log of c, the constant. Because c is a constant and the natural log of c is a constant. And the reason why I'm doing that is because in the next step, in order to solve for y, we have to undo the natural log of x. And we could do so by making e the base of both sides of the equation. So we'll take e to the natural log of y equaling e to the negative x cubed plus the natural log of c. So this is what I sometimes will refer to as Eulerizing, because e is for Euler, of course. And then we have our inverse property that e to the natural log of x is equal to x. And so e to the natural log of y is just y. And then on the right-hand side, there's something we could do as well. And that is to use the fact that since e is a base raised to a power, we can consider the basic law for multiplication of common bases, that is x to the a times x to the b is x to the a plus b. So if I treat e to the negative x cubed plus the natural log of c, in reverse I would have e to the negative x cubed times e to the natural log of c. But then the natural log, e to the natural log of c is just simply c, and so therefore this becomes e to the negative x cubed times c which we could just simply write as c e to the negative x cubed. Okay, so let me separate the little comments here. Alright, so all of those things were kind of separate ideas. Okay, to example number 2. First step, let's get rid of these radicals. So we'll say dy dx is 3, and then that would be the square root. If you think of the square root of xy, the xy is a quantity to the 1/2, but then we could express that as the product of x to the 1/2 and y to the 1/2. Okay, I always like to go to differential form, and again, it feels like you're multiplying by dx, but really what's happening is you're just using the definition of differential form. So I like to first express in differential form. Alright, and then at that point, to get the y's with the dy's and the x's with the dx's, we'll just divide both sides by y to the 1/2. And again, you could show it explicitly or do it mentally. So we have dy over y to the 1/2 equaling 3x to the 1/2 times dx. And the variables are actually separated now. So we've got the y's with the dy's and the x's with the dx's. Now in order to integrate dy over y to the 1/2, because there's a power in the denominator of y, you want to swing that up to the numerator. And let me throw the integral symbol in front of each side as well. So we're going to integrate y to the negative 1/2, and then integrate 3x to the 1/2 with respect to x. Alright, now we can integrate, so y to the power 1 greater, positive 1/2, divided by that new exponent is equal to 3 times x to the power 1 greater than 1/2 is 3/2 divided by 3/2 at our constant of integration. Notice I just added c because there was not a natural log generated on this side. If there's a natural log generated, we're going to add the natural log of c as our constant, for reasons as we did in the first example. Now, at that point, reciprocating the 1/2, we get 2y to the 1/2 equals, reciprocating 3/2, we get 3 times 2/3, or 2, and then x to the 3/2 plus some constant. And now we see we need to solve for y. And so to solve for y, actually, let me call this, I'm going to call this c sub 1. And then to solve for y, I'm going to divide everything by 2. And we get y to the 1/2 equals x to the 3/2. And then I'm just going to call this c, because c sub 1 divided by 2 is just a new constant. And now I'll call that c. And then to get rid of the 1/2, we'll square both sides. So y would be the quantity. Okay, so those are a few examples where we found the general solutions involving the constant c. And now we'll take a look at some examples that use the same method, separation of variables, but now define the explicit solution to an initial value problem. So we have initial conditions involved. Now, when we look at this first example, on the right is a function of x and y that contains 2 terms. And recall that in order to separate the variables, we need that expressed as a product of a unique function of x times a unique function of y. And what we can do in this case, well, there's actually a mistake in the given problem. This should be x squared. I apologize for that. Or I'm sorry, 2xy squared plus 3x squared. That's not an x squared. This should be a y squared. Okay, so make sure you make that correction. So again, the function is 2xy squared plus 3x squared y squared. So as I was saying, this is a sum of 2 terms. We have to make it a product of a unique function of x and a unique function of y. You can see why that needs to be a y squared, because we'll factor it out. And we get 2x plus 3x squared in parentheses. So now we can express it in differential form. Separate the variables, and do this mentally, just divide by y squared. That's 2. In order to integrate dy over y squared, we'll have to bring the y squared up to the numerator. And let me throw the integration symbol in front of each side, because we'll be ready to integrate at that point. So y to the negative 2 dy is the integral of 2x plus 3x squared dx. Integrating y to the negative 2, we get y to the negative 1 over negative 1. Integrating 2x, we get 2x squared over 2, or just x squared. Integrating 3x squared, we get 3x cubed over 3, or just x cubed. We'll introduce our constant as c. This would be negative 1 over y to the first, or just negative 1 over y. squared plus x cubed plus c. And to solve for y, we could reciprocate both sides and also multiply by a negative. So y would be, say, negative 1 over the x squared plus x cubed plus c. And that is our general solution, explicit, because y is solved explicitly in terms of x. And now to find c, the initial conditions are that y of 1 is negative 1, which means that y is negative 1 when x is 1, so negative 1 equals 1 over one squared plus 1 cubed plus c. So then we have that negative 1 equals negative 1 over 2 plus c. So negative 2 minus c is equal to negative 1, multiplying both sides by 2 plus c. So then moving negative 2 over, we get that negative c is power of 1, so therefore c is negative 1. And so then finally our explicit over plus x cubed minus 1. Okay, so you could do your algebra a lot of different ways. It's your choice. Don't think that what I'm showing you exactly what you need to do. There's a lot of delay in this, I apologize. Okay, so now we have a second example. Again, is a situation where the right-hand side needs to be factored. Squared, and we're left with 3y squared. And let's factor as well as the x squared. Draw to 3 squared, and then we'll be left with y squared plus 1. Okay, in a different form, dy would be 3x squared times y squared plus 1 dx. And separate variables, dividing by y squared plus 1, we have dy over y squared plus 1 equals 3x squared times dx. At that point, I'm actually going to throw the integration symbol in front of each side. The right-hand side is readily integrable, but the left-hand side, you may not recognize this integral. And from Calculus 2, you should recall this graph. Okay, from Calculus 2, typically we look for the integral of du over u when we see a fraction, which results in the natural log of the absolute value of u. But that's a problem because if we take u to be the denominator, the derivative is 2y, and there's no y in the numerator to help satisfy the du. So you should recall that if it doesn't fit the basic form of du over u, we turn our attention to the inverse trig functions, the integrals that result in the inverse trig functions. And the one in particular, with the sum of squares in the denominator, is du over u squared plus a squared, which results in 1 over a times the inverse tangent of u over a. So in this particular case, we have, and I'm going to do the work for this off to the side here on the scrap paper. We have our dy over y squared plus 1, where we could take our u squared to be y squared and our a squared to be 1. So u is y, a is 1, our du is just 1 dy. So there's no modification by a constant multiple necessary. We could change this to identically be the form of du over u squared plus a squared, which results in 1 over a inverse tangent of u over a. And if a is 1, we'd have 1 over 1 or 1, and then the inverse tangent of u is y over a is 1, or just y. So that left-hand side integrates to be the inverse tangent of y. So there's an integral that is a little bit more obscure. But then integrating 3x squared, we get 3x cubed over 3, or just x cubed. Introduce our constant, call it plus c. And then at that point, to solve for y, we're going to have to undo the inverse tangent by taking the tangent of both sides. So we could say that y is the tangent of x cubed plus c. And that's our general solution. Now for the particular solution, again we use the initial conditions. We're given that y of 0 is 1. So then 1 is equal to the tangent of just c, because if x is 0, that argument is just c. And then we're looking for the angle such that the tangent of the angle is 1. So you could do the inverse tangent, use a calculator, however you want to go about it. That's 45 degrees or pi over 4. So then our particular solution would be that y is the tangent of x cubed plus pi over 4. Okay, a couple more examples. This number 3 has a little bit of a trick to it. I have to go to scrap paper to show you the trick, because it's going to be hard to fit it all in here. The idea is, because this needs to be, remember, the right-hand side needs to be a product of a function of x and a function of y. What we could do here is use the property, I'm going to say e to the a times e to the b is e to the a plus b. So let's just multiplying common bases like we did with the x's, but e is the common base in this case. So the trick is this e to the 2x minus y, I'm going to break up to be the product of e to the 2x times e to the minus y. Because multiplying common bases, we would add the exponents. So that's a little trick to break that down to be a product of a function of x and a function of y. So we'll write 2y dx equals 6 e to the 2x times e to the negative y. I'll go to differential form. So dy equals 6e to the 2x e to the negative y. Dividing by e to the negative y, we get dy over e to the negative y equals 6 e to the 2x. And then to set this up so it's integrable, let's move this e to the negative y to the numerator as e to the positive y. And I'll throw the integral symbol in front of both sides at that point. Alright, and now we can integrate. the integral of e to the y is e to the y. And then you should recall this special integration for e to a linear power. And again, here's some scrap paper. The formula we should recall there is that the integral of e to the kx is 1 over k times e to the kx, and then plus or constant. So integrating e to the 2x, we get 1/2 e to the 2x. We'll add our constant of integration. So therefore e to the y is 3 e to the 2x plus the constant. And now we need to solve for y. And so to undo e, we'll take the natural log of both sides, because recall we have the inverse property that the natural log of e to the x is x. So if we take the natural log of e to the y and the natural log of this side, natural log of e to the y is just simply y. So y is the natural log of the quantity 3e to the 2x plus c. And that again is our general solution. So to find the particular, initial condition was that y of 0 is 0, which means that 0 is equal to the natural log of, well, this would be 3 plus c, because if we're putting a 0 in for x, then this becomes e to the 0. And then to solve for c, the base of the natural log is e to the 0 power is 1, is going to be 3 plus c. So therefore c is a -2. So then we get our particular solution that y is natural log of the quantity 3 e to the 2x minus 2. Okay, so final example for separation of variables, number 4 here. Again, we'll need to factor, in this case just a y. Left with 4x cubed minus 1 in parentheses. Differential form, dy equals y times 4x cubed minus 1 times the differential dx. Modifying by the y, so dividing both sides of the equation by y here. We get dy over y. 4x cubed minus 1. Should keep the parentheses around that because it's in differential form times the dx. Looks like we can integrate, because remember, if y is x or y in the denominator of the first power, that results in a log. So maybe if you want, integral 1 over y dy equals integral of 4x cubed minus 1 times the differential dx. Okay, so we get the natural log of y. Remember, we don't need the absolute values. We assume y is positive. And that's equal to integrating the right-hand side 4x to the 4th. 4x cubed integrates to be 4x to the 4th over 4, or just x to the 4th. The -1 integrates to be -x. And then here, again, like the first example that we went over on the previous page, since we generated a natural log on the left, we're going to express the constant as the natural log of the constant. because now we're going to Eulerize or take E to be the base. Of both sides of the equation. And so then e to the natural log of y by the inverse property is y. And then what we're going to do here is we're going to rewrite this by using the fact that, as we talked about on the previous page, if you consider, for example, our rule for multiplying common bases in reverse, e to the a times e to the b, so I've got scrap paper out here to illustrate this rule once again, e to the a times e to the b is e to the a plus b. We're basically taking e to the x to the fourth minus x plus the natural log of c, and we're going to split it up at this point. So this x to the fourth minus x is going to be the a, and the natural log of c is going to be the b. So this becomes e raised to the x to the fourth minus x times e to the natural log of c. But then by our inverse property, the e to the natural log of c is just c, so this becomes c e to the x to the fourth minus x. And now we can solve for the constant c. So again, that's our general solution. For the particular, the initial condition was that y of 1 was 3. So then 3 is equal to c e to the 1 to the fourth minus 1. But 1 to the fourth minus 1 is 0, e to the 0 is 1, so c is 3. And so then our particular solution is y is c, 3, e to the x to the fourth minus x. Okay, so that's our particular solution for that one. I forgot to note in the other ones, our final answers are the particular solutions. That should be obvious, but if you want to go back and label them, as our particular solutions. And then here, this one kind of ran out of room, but that's our particular solution. Okay, so we'll stop right there, and then we'll come back and we'll do the applications that are related to separation of variables.